So now we are going to start 16th problem, which is from 1993 AIPMT. If the temperature of the sun is doubled, the rate of energy received on earth will be increased by a factor of a direct problem from Stephen's law. We know that energy radiated by any source depends upon the fourth power of absolute temperature. If initially it was E and proportionality constant, we know that sigma. Now you are making temperature double, means to T you are making 2T. So clearly you can see that E dash is equals to 16 times sigma T4. And what is sigma T4? Initial energy. So by what factor energy is increased? Definitely by 16. It will become 16 times. So now moving to 17th problem. A beaker full of hot water is kept in a room. If it cools from 80 degrees centigrade to 75 degrees centigrade in T1 minutes, from 75 degrees centigrade to 70 degrees centigrade in T2 minutes, from 70 degrees centigrade to 65 degrees centigrade in T3 minutes. What is the relation between T1, T2 and T3? They asked this problem in 1995 AIPMT. We know that it is from Newton's law of cooling that rate of cooling is directly proportional to mean temperature minus temperature of surroundings. In this, what you are observing, 80 to 75 means difference is 5 degree. In a time T1, it should be proportional to 80 plus 75, 155 divided by 2. 155 divided by 2, it means 77.5. 77.5 minus theta. Next, again difference is 5 only, 75 to 70, 5 upon T2. It is proportional to now 75 plus 70 means 145 means 72.5 minus theta. Next, 70 to 65, again it is 5 upon T3. It is proportional to 70 and 60, 135. 135 means 67.5 minus theta. So what you are observing here, since this term is decreasing, it is decreasing. So it means it should be in decreasing order. If number is decreasing, it means denominator is increasing. It means T3 is greater than T2 and T2 is greater than T1. What we are observing here, right hand side is decreasing. Theta is fixed, 77.5 minus theta. Now difference is reduced. Again difference is reduced. And left hand side is directly proportional to right hand side. If right hand side is in decreasing order, left hand side should be in decreasing order, and the ratio will decrease. Either decrease numerator or increase denominator, but numerator is not decreasing. It means in this case denominator is increasing. So T1, T2, T3 should be in increasing order. So we are going with option A. Next, it is from 1997 AIPMT. A black body is at a temperature of 500 Kelvin. It emits energy at a rate which should be proportional to, clearly again a problem from Stephen's law. Radiations are proportional to fourth power of absolute temperature. Temperature is given in Kelvin only, so we can take this value 500. So it should be proportional to 400 raised to the power 4. So we are going with option B. Next is from 1998 AIPMT. What is the problem? The radiant energy from the sun incident normally at the surface of earth is 20 kilocalorie per meter square minute. What would have been the radiant energy incident normally on the earth if the sun had a temperature twice of the present one? See, first take care of units. Initially, radiant energy was in kilocalorie per meter square per minute. All four options are in same unit. So no need to conversion of units. So only now we have to take care of number. Initially it was 20 calorie per meter square. I am taking initially E1. We know that by Stephen's law E should be proportional to T raised to the power 4. It should be proportional to T raised to the power 4. Means radiant energy is equals to Stephen's constant multiplied by T raised to the power 4. If initially it was E1, temperature was T. Now I make the temperature double. So E2 should be equal to sigma 2T raised to the power 4. Means it should be equal to 2 raised to the power 4, 16. Sigma T raised to the power 4. And what is sigma T raised to the power 4? Initial value E1. E1 is given. In which unit E1 is given? By multiplying by 16, in same unit you will get E2. So what should be E2? 16 times of E1, and E1 was 20. So in same unit E2 should be 320 kilocalorie per meter square minute. So we are going with option A. Next, it is from 2002 AIPMT. For black body at temperature 727 degrees centigrade, its radiating power is 60 watt and temperature of surrounding is 227 degrees centigrade. If temperature of black body is changed to 1227 degrees centigrade, then its radiating power will be, since the temperature of surroundings is given, it means problem is related to Stephen-Boltzmann law. What is Stephen-Boltzmann law? E should be directly proportional to T1 raised to the power 4 minus T2 raised to the power 4. Constant is same. Sigma T1 raised to the power 4 minus T2 raised to the power 4. What were the temperatures? First we will write what is given. Initially temperature was 727 degrees centigrade. 720 degrees centigrade corresponds to, at 273, you will get 1000 Kelvin. 7 and 2, 900. 900 plus 100, which will make by 27 and 73. And the temperature 227 of surrounding, which is constant in both the cases. It corresponds to 273. When you will add 224 and 15, you will get 500 Kelvin. What about 1227? This degree Celsius, 1200 plus 200, 14 and 1, it will correspond to 1500 Kelvin. So what we are observing now, initially E1, I am taking E1 60 watt, E2 we want to calculate. What should be E1? Sigma T1 raised to the power 4 means 1000 raised to the power 4 minus T2 raised to the power 4 means 500 raised to the power 4. What is E2? Surroundings are same, only we make 1000 1500 minus 500 raised to the power 4. We want to calculate E2, so divide E2 by E1. See what we are going to get. E2 by E1 means 1000 raised to the power 4 minus 500 raised to the power 4 divided by 1500 raised to the power 4 minus 500 raised to the power 4. See how I am calculating this. I am taking 20 common. These are present in all 4. So that term will be cancelled out. 100 raised to the power 4. What is remaining now? 10 to the power 4 minus 5 raised to the power 4 divided by 15 raised to the power 4. Again I am observing that 5 can be taken common. So what we are getting now? Number will become smaller, so easy to calculate to save our time. Take 5 common, 5 raised to the power 4 will be cancelled out. So 2 raised to the power 4 minus 1 raised to the power 4 divided by 3 raised to the power 4 minus 1 raised to the power 4. 16 minus 1 is 15, 81 minus 1 is 80. What we are getting? 2 to the power 4 minus 1. Actually, we are putting E2 in denominator, so we have to reverse. It is not E2 upon E1. We did this E1 upon E2. What we did? We calculated E1 upon E2. We divide first equation by second equation. So we are getting here E1 by E2. What we got here? E1 by E2. No problem. We will cross multiply. So what is E2 now? E2 means E1 into 80 divided by 15. E1 was given 60 into 80 by 15. So what we are going to get? 15 fours are. So we are getting 320 watt. So we will go with B option, 320 watt. Next, it is from 2002 AIPMT. Problem was very simple. They are just asking for unit of Stephen's constant. You know, what was E? E was energy radiant by the source per unit area per second. It was sigma T to the power 4. So what was the unit of E? it is energy. Energy's SI unit is joule. Per unit area, per unit time. And what is the unit of temperature? Kelvin. Kelvin raised to the power 4. Joule per second is watt. So what we are getting? Watt per meter square. Take meter in numerator. Joule upon second watt. Take K4 at this place. So it will become K raised to the power minus 4. It is the unit of sigma. Watt meter raised to the power minus 2. K raised to the power minus 4. So we are going with C. So correct answer was C. Next, it is again from 2007, a same type of problem. A black body is at 727 degrees Celsius. It emits energy at a rate which is proportional to. We know that E is proportional to T raised to the power 4. Since we are using capital T, temperature should be in Kelvin. So in Kelvin, your temperature is 727 plus 273. What we are going to get? 729, 9 and 1000. So it is 1000. So it means E is proportional to 1000 raised to the power 4. So what we are going to get? 1000 raised to the power 4. So it was asked in 2007 AIPMT. So now we are moving towards 2009 AIPMT. A black body at 227 degrees Celsius radiates heat at the rate of 7 calorie per centimeter square second. Take care of unit. At a temperature of 727 degrees Celsius, the rate of heat radiated in the same units will be, no tension, they are talking about same units. We know the problem is related to Stephen's law because temperature of surrounding is not given. So initially we know that what is Stephen's law? E is proportional to T raised to the power 4. Means E should be equal to sigma T to the power 4. Initial value of E, I am taking E1. So what was E1? Sigma. What was temperature? I am writing here. Initially temperature was 227 plus 273. 200 and 204 and 1, it is 500 Kelvin. What was final temperature? 727 plus 273. 7 and 2, 9, 9 and 1, 1000 Kelvin. So now, E1 is equals to sigma into 500 raised to the power 4. What is E2? E2 is sigma 1000 raised to the power 4. We want to calculate E2, so divide E2 by E1. Sigma will be cancelled out. Power is same, so I am writing both terms in one bracket and putting power on that bracket. So I am getting this raised to the power 4. E2 corresponds to 1000. E1 corresponds to 500. 500 2s are 1000. So what we are getting? We are getting E2 is equals to E1 into 2 raised to the power 4 means 16. So what unit you are putting for E1? You will get for E2. In same units we want to calculate. So I am writing only number 7. And you know the table of 7. 7 16s are 112. So we are getting 112 calorie per centimeter square second. So we are going with option C. Next, two wires A and B have the same length and area of cross section, but Young's modulus of A is 2 times the Young's modulus of B, means different material we are using. Then the ratio of force constant of A to that of B is, what is force constant? Anywhere when you are talking about force constant, it is related to force required for unit extension. Either you are talking about at the atomic distance, you want to increase the distance between the atoms, you want to increase the distance of spring, you want to increase the length of any wire. Force constant corresponds to force required for unit extension. So what you want to calculate, right on left, you want to calculate F by delta L. What is the formula for Young's modulus? We know that Y is equals to FL divided by A delta L. So it means F by delta L, it should be equal to Y A by L. So now in first case, I am writing this F upon delta L K1. It was YA divided by L. In second case, what is the change in scenario? I am writing it K2 for F by delta L. What is the change? They are saying that Young modulus of A is 2 times the Young's modulus of B. First case means I was talking about A. Now I am talking about B because we want to calculate the ratio of A to that of B. So if Young modulus of A was 2 times the Young modulus of B, it means Young modulus of B was half of the Young modulus of A. For A, if I am taking Y, for B I should take Y by 2. What is A now? They are saying area of cross section is same, so we will put A. What about length? They are saying same length, so I am putting L. So what I am getting, YA by L means K1 is there. Additional I am getting 2. So what is the ratio of K1 and K2? So K1 by K2, force constant for first upon second, take 2 on this side, is 2. So we are going with option B. Next, if the ratio of lengths, radii and Young's modulus of steel and brass wires in the figure are A, B and C, then the corresponding ratio of increase in their lengths would be, means length of brass is A times that of steel. They are saying lengths, radii and Young modulus. First we write. We want to ignore any negative markings. What they are saying, we will write first. They are saying the ratio of lengths. First I am talking about length of steel and brass. Ratio of length of steel and length of brass is A. Radius of steel upon radius of brass is B. Young's modulus of steel upon Young modulus of brass is C. What we want to calculate, the increase in their length should be. So first I am writing it for steel. What is the formula for Young modulus? FL upon A delta L. First I am writing general formula, y is equals to Fl upon A delta L. Force is in the form of weight. So I have to use in place of F, mg, mgl upon A delta L. Since radius is given, so I have to use the formula in place of A, pi r square delta L. So increase in length, I got the formula for increase in length. It should be mgl divided by, I am taking delta L on that side, pi r square y, pi r square y. So by using this formula, first I will calculate change in length for steel, then I will go for brass, then I will find the ratio. First I am calculating it for steel. So what I have to use? Mass. See, the mass or weight responsible to increase the length of steel is not only m. 2m is also pushing this wire in downward direction. Also it is pulling the wire in a downward direction. This m plus this 2m. Both are pulling the steel wire in downward direction. So mass responsible is 2m and m, 3m. So in place of m, I am writing 3m. G. What is the length? Length I am writing ls. We are talking about steel. Upon pi, pi is same. I am writing r steel. What is y? I am writing y steel. Now I am calculating delta L for brass. To brass, the stretching force is only 2m. This m cannot increase the length of brass wire because only 2m is pulling this brass wire in downward direction. So responsible mass is 2m. So I am writing 2mg. Only this point you have to take care. Lb pi rb square into yb. Now divide delta ls by delta lb. See what we are going to get. First I am writing 3mg ls divided by pi rs square ys into, I am reversing the ratio of delta lb. Pi will go in numerator, rb square yb divided by 2mg lb. So cancel the common terms, mg with mg, pi with pi. So what we are getting, delta ls upon delta lb is equals to, number is 3 by 2, means either B option should be correct or C option should be correct, because number we are getting 3 by 2. Now we will write this, because we have ls lb this type, ls in numerator, lb in denominator. So we are getting ls upon lb, one bracket. Next, yb in numerator, ys in denominator. So I am getting yb by ys, yb by ys. Same, rb is in numerator. So rb by rs, both power 2, both have power 2. So I am putting in one bracket and putting 2 on that bracket. Now we have to put the value only 3 by 2 Ls by Lb is given A. S by Yb is C, but it is reversed, so I am writing 1 upon C. Similarly, it is also reversed. Rs by Rb by B, so it should be 1 upon B, power is 2. So it means we need A in numerator, B square C in denominator, so going with option B. So option B was correct. Next, the shear modulus of a liquid is, what is liquid? You know the liquid. What is modulus of elasticity? Stress upon strain. Strain is in denominator. So if we are putting a small force only, what we will get? We will get a big change in that liquid. So for liquid we can take it nearly 0. The shear modulus of liquid is 0. Next, it is again a relation between y, eta and b. So I told you in theory, okay, what is the relation between this? Y is always 3 into bulk modulus 1 minus 2 sigma. Remember these two relation only, Young modulus, bulk modulus, Young modulus and coefficient of rigidity. All relation you can make with the help of these. If you don't want sigma, sigma is Poisson's ratio. Equate the two values of sigma. You will get relation between Yb and eta. And this is the relation between Y and bulk modulus, Y and eta. So by removing that, you will get this option. So we are going with D. Next, the length of a wire is L1 when the tension was T1 and length was L2 when the tension was T2. What is the original length? It means we are talking about same wire in both cases. Same wire in both cases, and we know that y is equals to FL upon A delta L. F means force. Force we are representing by tension. So it was tension. Suppose initial length of wire was L. Area of cross section was A. What they are saying, when tension is T1, the length of wire was L1. What is delta L? Delta L is original length plus change in length. They are saying initially it was L1. So what is delta L? Initially, in first case, delta L should be L1 minus L. So I am writing here L minus, initial length we are taking L, so it should be L1 minus L. In second case, we are putting tension T2, wire was the same L. Area of cross section was same, but due to this, length changed up to L2. So now change of length should be L2 minus L. Since both are Y, so by equating these two equations, what we are getting? T1L by A into L1 minus L is equals to T2 into L divided by A into L2 minus L. Cancel the terms common in both A and L. What you are getting? T1 into L2 minus L is equals to T2 into L1 minus L. This I am getting. means T1L2 minus T1L is equals to T2L1 minus T2L. We want to calculate original length. So take L on one side. So what we are getting, suppose I am taking this on that side. So I am getting L into T1 minus T2, because with L there is minus T2. T1 minus T2. On this side I am getting T1L2. T1L2 is this, I am taking this on that side, minus T2L1. So what I am getting L? I am getting L is equals to T1L2 minus T2L1 upon T1 minus T2. But this type of answer is this only, so no need to be tensed. Take minus sign common from numerator and minus from denominator. Minus will be cancelled out and you will get T2L1 minus T1L2 by T2 minus T1. Means same answer you can write like this also, and it is given there T2L1 minus T1L2 upon T2 minus T1. So we are going with option C. Next, the mean distance between the atoms of iron is this, and the interatomic force constant for iron is this. The Young's modulus of elasticity for iron is. What is happening in a wire when you are applying a force? Actually, atoms are arranged in a wire like this. Imagine one cube, and at each vertex one atom is there. At each vertex imagine one atom. I am only making this structure for this 8 atoms. When you are applying a force, you are increasing the interatomic distance. If initially it was R0 and you change this length to R0 plus delta R0. What is the stress? Stress is force per unit area. Area means this square's area. So it should be R0 square. What is the strain? It is stress. What is strain? Strain means change in length upon original length. So what should be the value of Young modulus? Stress upon strain. F upon R0 square divided by strain means into R0 upon delta R0. Cancel one R0. I told you initially that force required for unit extension anywhere is known as force constant. It means when you applied force F, the extension in the length of atoms means interatomic distance is increased by delta R0. It means to increase the interatomic distance by delta R0, you need a force F. So for unit extension, you need a force of F upon delta R0. It is known as interatomic force constant. So it means what we are getting this interatomic force constant. So remember, one important relation is this: interatomic force constant is Young's modulus multiplied by interatomic distance. So in this problem, R0 was given, interatomic force constant was given. You want to calculate Young modulus. So for this problem, I am writing is y is equals to k upon R0. What is k? SI unit 7. What is R naught? Again in SI unit. 3 into 10 to the power minus 10. Take minus 10 in numerator. 3 2s are 6. 2.33 into 10 to the power 10 Newton per meter square. So what we should go for? D option. 2.33 into 10 to the power 10 Newton per meter square.